we talked about speed, and speed can be calculated using an equation. It's just a little division problem. Distance divided by time, right? So you've probably heard of the term velocity, and velocity and speed are closely related, but what velocity does is give how fast an object is moving and also give the direction that it's moving. So the big difference is velocity gives both speed and direction. So if velocity gives direction, here in a minute you're going to see velocity is great with, you can just kind of picture velocity if you use an arrow. For instance, we would say a car is traveling 45 miles per hour, that's speed. But if we add to the speed the direction that the car is moving, now we know the velocity of the car. Okay, not any big hairy deal. So not only is it moving 45 miles per hour, but it's moving in a direction of northeast. So now we know the velocity of the car. So they are two different things. I guess speed is basic and velocity is speed plus direction. So as I said, kind of arrows work great for showing direction. Just kind of like arrows work great for showing the direction of a force, arrows work great for showing direction of motion. So here we have direction kind of, this could be our northeast 45 miles per hour. This could be our northeast at, what do you think, maybe half that, maybe 20 miles per hour. This could be our due west at maybe 50 miles per hour. And this is going in a circle. Let's go ahead and take a look at this motion. The direction that this motion is going actually would be changing. So for instance, if this is A and this is B, okay, so here early on in the motion of this, let's make it a car, notice that the car was traveling in this direction. If we kind of go here at this point, the car is traveling at this direction. At this point, the car is traveling at this direction. Okay, at this point, the car is traveling at this direction. Kind of get the idea. What I'm doing or trying to do actually is drawing an arrow, drawing a line that is what we call tangent to the curve of that motion. And then up here, it's finally going here. So can you see where throughout the path of that motion, that car actually has changed its direction kind of continually? So that is circular motion. There's also an important, there's another important word connected with motion, and that's called acceleration. And you're probably already familiar with it. When you drive a car, you hit the gas and you accelerate? You let up on the gas and you decelerate, you slow down. Acceleration by definition means that the velocity is changing. And so if velocity is actually two components, velocity is speed and direction, if we change velocity, okay, we could be doing one of three things. Well, more than I guess one of three things. We could actually be going faster in our speed. We call that acceleration. We could be going slower in our speed. Now again, I'm not even focusing on direction. We could stay in the same direction and speed up or slow down, and we are accelerating. Or we could be going the same speed and moving in a different direction. That's also acceleration. So in other words, we're used to thinking of the car with the gas pedal, accelerating, decelerating, but also think of acceleration if you hold the same speed and you're going around a curve. If you're navigating a curve in your car, then you are at constant speed, you are accelerating. So I have some examples. Your textbook has some examples of accelerating. So here we have, let's see, let's kind of look at this together. We've got the initial velocity. Actually, here in a minute, we're going to call that V sub initial. Subscripts work great for relaying a lot of information. And here we have the final velocity, V final, is equal to 20 kilometers per hour. So clearly it's sped up. And in order to, here in a minute, do acceleration calculations, we're going to need to know the time interval over which that speeding up occurred. So here we don't have it changing direction per se, but we have it changing speed. Okay, and here they're showing it not speed but velocity because we're also, it's implied we know the direction of this motion. So that's acceleration, increasing speed. Decreasing speed is also acceleration. I know it says deceleration, but I'm hoping that we can kind of get into the thought process that deceleration is, in terms of physics, also changing speed. It's just speed that's getting less, and that is a form of acceleration. So in the case we have the initial velocity is greater than the final velocity. And notice that this is just a kind of a continuation of the same problem. So we have a 1 second interval over here, and we actually have a 1 second interval over here for the deceleration. This is an example where notice that the car is coming to a stop sign and the final velocity is 0. And then last but not least, I'm bringing in an image of a car that is going in a circle. So a car going in a circle, let's assume that it is going at constant speed, okay, but its velocity is changing. Because remember, velocity is speed and direction. Because its velocity is changing, because its direction is changing. And if its velocity is changing, that means that we have, dun dun dun, by definition, we have acceleration. Okay? So we're going to do some kind of hopefully straightforward, simple examples here. We do have another little equation, and usually, and I think I'll probably do it again this semester, I give you an equation sheet for physics, and so I will actually give you this equation. Notice that we're dealing with not just any acceleration, but the average acceleration versus the instantaneous acceleration. And we're going to take whatever its final velocity is, we're going to do a subtraction in the numerator. We're going to take the difference of the final velocity minus the initial velocity. In science, we always we always take the final state and from that subtract the initial state. We just always do that. Divided by time. So it shouldn't be too bad. We could go back and do those ones on the previous slide if we wanted to. We can rewrite this equation to look like this. So anytime you see, this isn't like just another little science hint, anytime you see a bar over a variable, the variable for acceleration is the lowercase a, with a bar means average. And notice also we've kind of abbreviated the, instead of final we put the letter F, instead of initial we put the letter I, instead of time we put the variable t. One more thing I kind of want to throw at you. Anytime you have a difference like this, like you have up here, okay, you can, how do I say, change, you can replace that difference, you can use the symbol delta was my point here. So, not just any difference, I should say, this is the change in velocity. So anytime it's the change in, you can actually, instead of writing change in, use a triangle, and the triangle is the Greek letter delta, and that means change in. So here we have kind of a final summarized one version of calculated acceleration. Acceleration is the change in velocity divided by the change in time. So let's do one. We know we've got velocity here because it looks like we've got direction, which is due north, and it's going to stay due north. And then we've also got speed. So let's go ahead and I'll draw my car. Oh my goodness, that's a strange car. Okay. Okay, so we'll go ahead and from left to right, this is A. Okay, and then over here is going to be my B car. Draw my little, don't forget the wheels. Okay, it's traveling north. We'll make this north. And it's beginning from rest. So I'm going to see how kind of pictures help. So I don't know if it helps you or not, but beginning from rest. So actually I'm going to go ahead and put my velocity sub I, my initial velocity is 0. I'm going to put my units here in a minute when I see what my units of my final velocity is. And then the problem goes ahead and says in 3.4 seconds. So I'm going to go ahead and I'm going to put t is equal to 3.4 seconds. It is finally traveling at, so that's going to be my v sub f, at 15 meters per second. Cool. Looks like I can do that. If we go back a slide, you see that the equation we have is acceleration is equal to v sub f minus v sub I, final velocity minus initial velocity divided by the time over which the acceleration occurs. So it's not too bad. What I'm getting is 0. Oops. The final velocity is 15 meters per second. 15 meters per second minus, it started at 0 meters per second divided by the time the acceleration occurred, 3.4 seconds. All right, get out the old calculator here. That's like 15 minus 0 is 15. So I'm just going to take 15 divided by 3.4, and I get 4.41176, blah, blah, blah. So I'm going to write my answer up here. Okay, I ran out of room. I got acceleration is equal to 4.4117. 4.4117. Now units, because I say don't forget your units, is going to be meters per second in the top and second in the bottom. So it looks like this, meters per second per second. Okay. So a few things about that, and actually we're on the right track, so don't worry. I'm going to go ahead and I want to round it better. So let's see. I'm kind of thinking 2 digits up here-ish and 2 digits down there. I'm thinking I'm only going to take 2 digits. So actually I'm going to go ahead and round that to 4.4. Now let's take a look at our units. So we got units of meters per second, and you can actually leave it that way, or you can go ahead and combine these seconds, and they actually will combine, not cancel, and to give you seconds squared. So another way to do that would be meters per second squared, and kind of squeezing it in there, but actually that's a good solid answer. So I want to give you this as a video question, and just kind of do your best, and it should be kind of similar to the one we just did, but notice that you'll probably come up with how do I say this? Your acceleration will be negative because it's decelerating. So the negative actually will carry along in the problem. That's my hint. Take a look at the assignment that you've got. Notice I went ahead and brought in, for the first assignment anyway, you have two assignments. You have question, well, not two assignments, but you have two questions. Problem 12 and problem 14. So problem 12 is here. And I don't think I have a whole lot to add. I'll just kind of point out that problem 11, I believe, is very similar. And you have the answers to problem 11. And problem 14 is here. Okay, if you have questions, give me a call or kind of ask them. Remember, on Thursday night the homework is due, but you can also, we have kind of a question and answer at the end of the evening after lab on Thursday night.